Hello friends, I welcome you in lecture number 21 on group theory. In this lecture we will discuss one question on finding left and right cosets of a subgroup. This question was asked in GTU Summer 2021 exam. And we will use these two properties which we are familiar with to decide the left and right cosets. If some element A is present in the subgroup, then left coset corresponding to that element is subgroup itself. Another property is if A1 element is present in the left coset A2H, then left coset corresponding to A1H and A2H are always equal. So these two properties will minimize our calculation in deciding the left and right cosets. Also we know that if our group is abelian, that is commutative, then left and right cosets are always equal. Now here our group is Z6, that is group generated by equivalence classes corresponding to 0, 1, 2, 3, 4 and 5. This is modulo group with addition modulo 6, and if you are not familiar with modulo group, I suggest you to watch my lecture on modulo group. So this is Z6 having 6 elements starting from equivalence class by 0 to equivalence class 5. And we know that this Z6 is an abelian group. Z6 under addition modulo 6 is abelian. So we don't have to calculate right cosets separately because this Z6 is abelian. Left and right cosets are always equal. Therefore, left and right cosets of subgroup H are equal. Okay, fine. Now we start from first element. We determine the left coset corresponding to each element of this group. So first we start with left coset corresponding to element equivalence class generated by 0, and we observe that 0 is present in the given subgroup. So using this first property, we can write that equivalence class corresponding left coset corresponding to equivalence class is H itself, because 0 is present here. So this is equal to H itself, and H is having two equivalence classes 0 and 3. So here, because this equivalence class generated by 0 is present in the subgroup, therefore left coset corresponding to equivalence class 0 will be equal to H itself. Second element is 1, and 1 is not present here in the subgroup H. So we use the definition to decide the left coset corresponding to this 1. So by the definition, this we can write as 1, and operation is addition modulo 6, and elements of subgroup are equivalence classes. So we write in this way: equivalence class generated by H, and here we write capital H. Now capital H has two equivalence classes, so we first write 0. For H equal to 0 we will have this element, and for H equal to 3 we will have this element. Now we use the definition of addition modulo 6. Addition modulo 6 says that we recall that operation. Suppose we have addition modulo n, then this is equal to equivalence class generated by a plus b modulo n, where this a plus b modulo n is the remainder when a plus b is divided by n. So using this definition, here we will have 1 plus 0 modulo 6 equivalence class generated by 1 plus 0 modulo 6, and here we have 1 plus 3 modulo 6. 1 plus 0, that is 1, and the remainder when 1 is divided by 6 will be equal to 1. Similarly, 1 plus 3 is 4, so remainder when 4 is divided by 6 will be equal to, just a minute, 1 plus 3 is 4, and 4, when 4 is divided by 6, remainder will be 4. And you can understand in this way also. 1 plus 3 is 4, and we divide 4 by 6. So suppose we multiply 6 by 0, here we will have 0. So remainder when 4 is divided by 6 is 4. Similarly, remainder when 1 is divided by 6 is 1. So in fact, if our integer is less than 6, then remainder will be that integer itself. So for 0, 1, 2, 3, 4 and 5, suppose we ignore 0, then for 1, 2, 3, 4 and 5, modulo 6 will be equal to these elements itself, that is 3 modulo 6 is 3, 4 modulo 6 is 4, 5 modulo 6 is 5, and so on. So we have obtained the equivalence class corresponding to 1, or we have obtained the left coset corresponding to the equivalence class generated by 1, and it is having two elements 1 and 4. Here we have 0 and 3, and we can write left cosets, right cosets also in parallel because they are always equal. So this is the left coset corresponding to equivalence class 0, and because our group is abelian, this is going to be right coset also. Same thing here, this is equal to right coset corresponding to equivalence class 1. Now we find left coset corresponding to the equivalence class generated by 2, and we can check whether 2 is present here or not. Here 2 is absent, here also 2 is absent, so we have to use the definition to obtain the left coset corresponding to equivalence class generated by 2. So by definition, this is equivalence class corresponding to 2 plus equivalence class corresponding to H, and this is an element of H. Now there are two elements in H. Equivalence class is generated by 0 and 3. So we substitute them here, and here I have to write addition modulo 6. This is 0, then 2, addition modulo 6, 0 and 3. Okay, we substitute these elements of given subgroup. Now by definition, this is 2 plus 0 modulo 6 equivalence class generated by 2 plus 0 modulo 6, and here 2 plus 3 modulo 6. 2 plus 0 modulo 6 means remainder when 2 is divided by 6, that is 2 itself. Here 5 modulo 6, that is remainder when 5 is divided by 6, which is 5 itself. And because left and right cosets are equal, we can write here this is the right coset corresponding to equivalence class 2, because our group is abelian. Now next element is 3, so we can see left coset corresponding to equivalence class 3 will be equal to H, because 3 is present in the given subgroup. 3 belongs to H. So using that property we can write that left coset corresponding to equivalence class 3 will be equal to H, and because group is abelian, this is right coset also. Then we take 4, so 4H, and we check whether 4 is present somewhere in any coset, and we observe that 4 is present in this left coset. So using that property we can write that this is going to be 1H, because this 4 equivalence class generated by 4 is present in the equivalence class generated by present in the left coset corresponding to 1. This 4 is present in this left coset corresponding to equivalence class 1, therefore these two are equal, and we have obtained this. The elements of this left coset corresponding to 1 are 1 and 4. So this is 1, 4, and because our group is abelian, this is right coset corresponding to equivalence class 4. And last element is 5, and this is present in this left coset corresponding to equivalence class 2. So because this 5 is present in this left coset corresponding to 5 will be this coset containing equivalence classes 2 and 5. So now we can write that since this 5 is present in the left coset corresponding to equivalence class 2, therefore left coset corresponding to equivalence class 5 will be equal to left coset corresponding to equivalence class 2, and this we have already obtained. It contains two equivalence classes 2 and 5, and our group is abelian, so we can write this is equal to right coset corresponding to this equivalence class 5. So in this way we can decide the left and right cosets, and if we observe the number of distinct left cosets, so one is class containing 0, 3, then 1, 4 and 2, 5. So there are 3 distinct left or 3 distinct right cosets of given subgroup, and remaining are repeated because these two are equal corresponding to 5 and 2. Similarly we can see that these two are equal left cosets corresponding to 4 and 1, and left cosets corresponding to 0 and 3 are also equal. So there are 3 distinct left cosets, and here we are asked to find out left and right cosets of H. So this finishes our answer. We have to just write down left and right cosets starting from 0 up to 5. Now one observation here is, here order of given subgroup, that is Z6, number of elements in Z6 are 6, and the number of elements in given subgroup are 2. We have 2 elements in the given subgroup, and we obtain 3 distinct left or right cosets. 3 distinct left cosets we have obtained, and we can see if I divide this 6 by 2 I will obtain 3. So the number of distinct left cosets is nothing but division of order of group and order of subgroup. If we divide the order of group here by order of subgroup, then we obtain the number of distinct left and right cosets. So this is not true for this is not only true for this particular example, but in general this is true. So we can make this type of remark. Suppose we have H as a subgroup of group G, and suppose number of elements in G. Here I will use another notation for the number of elements. This is another notation for the order of the group. Order of group means number of elements in a group. Suppose order of G is n, that is number of elements in G are n, and number of elements in H are m, then the number of distinct left or right cosets, the number of distinct left or right cosets of subgroup H in G is equal to n divided by m, or we can simply write order of group divided by order of subgroup. In our example, order of G is 6 and order of H is 2, and we have seen that we obtain 3 distinct left or right cosets. So remember this remark. This will be helpful to check whether your answer is correct or not. And this is true whenever order of group is finite. That is, whenever there are finite number of elements in your group, you can check your answer in this way. Number of distinct left or right cosets is always equal to order of group divided by order of subgroup, that is n divided by m. So here we obtain 3 distinct left cosets, and order of group is 6, order of subgroup is 2. So this must be 3, and we have obtained 3 distinct left cosets. So we can be sure that our answer is correct. Okay, fine. So this is all about this lecture. I hope you like it. Thank you very much.